Today we're doing section 2.2 quadratic functions, and this is the fourth day in this set of notes. So we are going to do more on the optimization example that we had in last night's video. I only got to go through one of them, so I'm going to do some more practice on those. So for this first example, it says you have 100 yards of fencing to enclose a rectangular region. Find the dimensions of the rectangle that maximize the enclosed area. What is the maximum area? So remember we discussed that you have to be able to find what you're trying to maximize, an area based or a formula based on the information that's given. So some information that's given is that I have 100 yards of fencing to enclose a rectangular region, and I'm trying to maximize the area. So that's the two pieces of information we're going to start with. So if I have a rectangle and I don't know either side, I can just assume that one side is X, one side is Y. And if I tell you that I have 100 yards of fencing, that means I'm telling you the perimeter. And we know the perimeter is adding up all the sides. So my first equation I would say is that 2x, actually let me write it below the rectangle, 2x plus 2y has to equal 100. And the second equation based on this picture is that I'm trying to maximize the area, and I know that the area is length times width. So based on this, x times y. So I'm going to go back to that first equation that we wrote, and we always solve for y. So the first thing I would do is subtract this 2x over. So I have 2y equals negative 2x plus 100. And then I'm going to divide both sides by 2. So y equals negative x plus 50. Now I'm going to take what I got for y and I'm plugging it into the y of the area equation. So I have a equals x times negative x plus 50. And I'm going to distribute that x in. So I'll get negative x squared plus 50x. And I know if I want to find a maximum, that's referring to the vertex. So I'm going to do negative 50 over 2 times a negative 1. So negative 50 divided by negative 2 is 25. So if x is 25, now I'm going to plug it into this equation for y. So I'll get negative 25 plus 50, which equals 25. So my dimensions of my rectangle are 25 by 25. And if I want to know the area, I multiply them together, and the final answer is 625 feet squared. So the next one is an example from the textbook, and I wanted to go over this one because I don't necessarily like the picture that they used. So it says you have 200 feet of fencing to enclose a rectangular plot that borders on a river. If you do not fence the side along the river, find the length and width of the plot that will maximize the area. What is the largest area that can be enclosed? So one thing I don't like in the textbook is that they write this 200 minus 2x. I would just call that this third side our variable y. So it's kind of the same idea as the last problem. It's just one of the sides is missing because it would be buddied up to a river. So for my perimeter, I would say 2x plus y equals 200. And the area formula is still going to be x times y. So I'm going to solve this equation for y. I would do that by subtracting the 2x. So I have y equals negative 2x plus 200. So I'm going to come over to our area equation, and I'm going to plug in the y for that. So I have negative 2x plus 200. And then I'm going to distribute this in. So I get negative 2x squared plus 200x. And now that I have this quadratic equation set up, I'm now going to find the maximum, which is referring to the vertex. So I'll have negative 200 over 2 times the negative 2. So negative 200 divided by negative 4 will be 50. So I know x equals 50. Now I'm going to come over here and plug x in. So I'll get negative 100 plus 200. So y equals 100. And the last question wants to know what is the max area. So I would do the 50 times the 100. So we'll get 5,000 feet squared for our maximum area. So we're going to go through one more together, and then that's going to be our last example. So our last example would probably be the most challenging one you would see. So it says a rectangular playground is to be fenced off by dividing in two by another fence parallel to one side of the playground. 400 feet of fencing is used. Find the dimensions of the playground that maximize the total enclosed area. So we're obviously dealing with a rectangle, and it says that they're going to add this parallel piece to kind of divide this into two playgrounds. So if we call this y, we know that this dimension is x. So when I go to write my equation for my perimeter, I'm going to have 3x plus 2y equals 400. And again, I know that the formula for the area is x times y. So I need to solve this equation for y by subtracting 3x. So 2y equals negative 3x plus 400. And then we're going to divide everything by 2. So y equals negative 3/2 x plus 200. And now we're going to plug that in for the area over here. So I have my area is equal to x times negative 3/2 x plus 200. And we'll distribute. So I'll get negative 3/2 x squared plus 200x. And now we find our vertex. So I have x equals negative 200 divided by 2 times the negative 3/2. So in the denominator, these 2's are going to cancel, and I'm left with a negative 200 divided by negative 3, which is equal to 66 point, we'll just say 7. Alright, so now we're going to plug it back in. Now, when I plug it back in, I'm going to actually leave it in fraction form because I think it'll be a little bit easier to do by hand. Obviously, you could use the calculator, but I think keeping it in fraction form is a little bit easier. So the 3's are going to cancel, and now I'm dealing with negative 200 divided by 2, which is negative 100 plus 200 equals 100. So if you use the decimal of 66.7, you probably got a decimal like very, very close to 100. Either you got like 99.99 or you might have got 100.3 or something like that. So that's why I said fraction form is a little bit easier. And then I have to find my area. So I'm doing 66.7 times 100, which would be roughly 6,670. What are we in? Feet squared. Alright, so that's all for today. We'll pick up with this tomorrow.